So in the last class we had looked at the different mechanisms of flux decline and fouling mechanisms and their models. What we had looked at was the dead end filtration, where different kinds of mechanisms of blockage happens, and then we had worked out expressions for how the flux declines or how the volume, or the cumulative volume or the flow rate declines with time, and we had expressed all that in terms of the flux change with respect to time. We had done a small problem also. We also saw different mechanisms for decline of flux in a cross flow filtration, and that was because of the concentration polarization, because of the osmotic pressure, as well as the gel layer formation. So we had derived an equation that allows us to calculate the polarization modulus, and we had done a problem based on that towards the end. So if you had done these two, you would have been able to regenerate this graph directly from the paper that is there. Okay. We had also looked at fouling, and we had looked at how to control the fouling. Let's put all these into a small problem, couple of problems. So first of all, imagine that an enzyme is being concentrated in a claustrum manner at some location in the module. The flux is 400 LMH and the mass transfer coefficient is 3 into 10 raised to minus 5 meters per second. Rejection is 0.95. I would like you to calculate the polarization modulus. So again, you should pause the video at this point of time. Try to look at the expressions, derive the answer yourself, and then only go forward. So what we had seen was the ratio of the membrane concentration of the solute near the membrane surface to that of the bulk. We had represented that, we had calculated, we had derived this equation based on the flux as well as the mass transfer coefficient. So if you substitute the values, you will be able to get the answer. So the flux here is 400 LMH, that is 0.4 meter cube per meter square hour, which is same as 0.4 meter per hour. So if we convert to meter per second, we'll have to divide by 3600, and then rejection is 0.95. If you substitute that, you will find that the polarization modulus is 13.6, which means the membrane concentration of the solute near the membrane is 13.6 times that of the bulk concentration. And you can see the very large problem that this would create for the membrane separation. In terms of how it will change the effective driving force, here is another problem. So imagine that an aqueous solution with an initial solute concentration of 0.02 molar is being concentrated to 0.1 molar. Let's say the transmembrane pressure is 3.5 bar, and imagine for simplicity that the polarization modulus is 1. So which means the membrane concentration of the solute near the membrane surface is same as the bulk concentration. I would like you to calculate the effective pressure driving force at the start and at the end of operation. Let's assume that the rejection is 0.95. Again, pause the video, do the calculation for yourself, and then only proceed forward. Right. So you would have seen that the effective driving force, remember we had derived this expression. Flux was delta P minus the osmotic pressure driving force. Osmotic pressure driving force was arising because the concentration in the permeate side is very small, concentration at the surface of the membrane is very large, and that creates a reverse osmotic pressure gradient which opposes the applied transmembrane pressure. And so if you put in all these values now, effective driving force is delta P minus delta pi, and delta pi is nothing but Cm minus Cp, the concentration difference across the membrane, multiplied by RT. We are of course using the Van 't Hoff equation, and if you substitute that in terms of the rejection, you will get 0.95, that's the rejection, into membrane concentration multiplied by RT. So if you substitute the values, you will find that the effective driving force is 3.5 minus 0.95, 0.02, 8314, 303, and if you use R in terms of units of joules per kilomole Kelvin, you will get the osmotic pressure in Pascal. So we'll have to divide by 1 into 10 raised to 5 to get it into bar, and then you will find that the effective delta P at the start is 3.02 bar. Similarly, if you put in all the values, you will find that the effective delta P at the end of the operation is 1.1 bar. So you will find that just by this change of as we are concentrating in the membrane, we are having an effective pressure difference which is reducing by a factor of 3. So the start and end, so if we are doing a batch operation, the pressure driving force, effective pressure driving force will reduce with respect to time. Or if we are having a membrane where there is a plug flow of the feed, from start of the module to end of the module, the pressure difference, effective pressure difference at the start of the module and end of the module will change from 3.02 bar to 1.11 bar. And then you can imagine what would be the effect of flux, how the flux will decline with respect to not time in this particular case because it's a flux flow manner, how the flux will reduce with respect to the location or length along the membrane module, and then we will have to integrate all this to get to either time if it's a batch process or to the total membrane area if we are looking at the flux flow operation of a membrane module. So we'll do all that in the next class once we see different kinds of membrane modules that are there.